Hey guys, in this video I'm going to talk about ping. We're going to cover what it is, what are the common uses, how does it work, and then we're going to be taking a deeper look at the packet level using Wireshark. Alright, let's begin with understanding what is ping. Quite simply, ping is a command line tool to test reachability of a device on a network. The device here could be any device like a computer, tablet, server, router, switch, etc. Basically anything that has networking capabilities. Let's talk about some of the features of ping. So although it's quite old, it's still very relevant and useful today. And the names such as ping, echo, and to some extent even the concept is inspired from sonar and the whole principle of echolocation. Ping can work on any operating system, whether you have a Linux, Mac, or Windows. You can also see this tool in most networking devices such as switches, routers, etc. And it works using ICMP. ICMP is a protocol which was developed for diagnostics and error reporting. And lastly, ping has no client-server model. It's actually a very simple 1:1 request-reply model. As an example, we have two devices here. So device A on the left is going to send an echo request and it's going to expect a reply, which device B is going to reply with an echo reply. All right, moving on to some of the common uses of ping. Well, the primary use of ping is to help in diagnosing and troubleshooting connectivity issues. It could be that you're trying to test reachability to a particular host or an IP address, or maybe you are experiencing networking issues or testing out a new network path or configuration. And there you can use this tool to figure out stuff very quickly. Ping could also potentially be helpful in detecting network performance issues like intermittent drops, high latency, random spikes, etc. And there are some services or applications which use ping packets to maintain the session with the host on the network. This really depends on the application's behavior though, and we call them keep alive messages. Now here are two snippets of the outputs of ping command. I ran on both Mac and Windows. The Mac output is on the left and the Windows one is on the right. There are some minor differences, but mostly it's the same characteristics mentioned in both outputs. Things like destination IP, bytes, round trip time or RTT. And we're going to be taking a look at this practically with Wireshark in just a bit. Let's now take a look at how ping actually works. Ping packets are nothing but pairs of ICMP echo requests and echo replies. ICMP does a lot more than ping, and in order to track the various kinds of packets, the ICMP header contains two fields, type and code. So for a device, say device A, sending an echo request, it's sending an ICMP packet with type 8 and code 0. That would actually signify an echo request. And the responding device, say device B, would reply with an ICMP packet with type 0 code 0, which means an echo reply. There are a few more considerations about this exchange. First being device B needs to reply to device A's request before the timeout. If that doesn't happen, we will see the timeout on the device A's console. Next, for each request, there must be one reply, meaning for a single request, there can only be a single reply. And if there are more than one, if say 4, 40, or even 4,000 requests, then an equivalent number of responses are expected. In order for the system to track the numerous requests, the requests are marked with an identifier and sequence numbers. That way, a system can easily identify and report which request went unanswered. Great. Now look at ping packets in Wireshark. Okay, so what I have here in front of me is a terminal. This is the default terminal on Mac. And if I want to issue some ping commands, what I can do is just type ping and type an address. Now, I could type an IP address or I could type an FQDN. So let's just ping Google and see what we get. Okay, so we go. We got ping google.com, which resolves to an IP address. This is done with the help of DNS. Everything on the internet actually lives on an IP address, IPv4 or IPv6, but we can't, of course, remember all the addresses. So we just use FQDNs and we use DNS servers to resolve So when I type ping google.com, the very first thing my system is going to do is actually going to resolve that google.com into an IP address that it can ping, and then it's going to send ping packets. And that's why sometimes you might see that the very first ping gets dropped, but then subsequent pings work just fine. That's probably because the response delay from DNS or maybe ARP or something. So that's fine. Another thing I want to point out here is that if you see I just issued the ping Google account once, and this is on a Mac, but the pings are running infinitely. And that's the default behavior. So on Mac and on Linux, basically anything Unix like, you'll see that the ping will run continuously. However, on Windows, if you were to run the same ping google.com, it will issue just 4 packets, or ping anything.com, like it will just issue 4 packets. If I want to stop this, I'll just type Control C. I should break the ping. If I want to issue only 4 ping packets, what I can do is I can just type ping google.com with a flag -C, C for count, and 4. So again, it will send the 4 ping packets and then it will auto terminate. Now let's do one thing. Let's send those ping packets and then look at them in Wireshark. So let me do one thing. Let me start my Wireshark capture. And I'm just putting a display filter for ICMP. Remember, ping is using ICMP. And now let me just clear the screen once and run the same google.com and run 4 pings. Done. So first impression here, you have 4 lines or 4 requests that we send, but here we're going to see 8 packets, right? Because recall, ping works as a pair of a request response. So 1 is a request. Let me just make this a bit bigger. And now let's look at all the details here. So the first ping packet here, let's bring this up. It's actually this one, 64 bytes from 172. This is actually a response that is showing me. And on the Wireshark, I can see my request. So let's bring it here. Okay. So this is the first packet. Now Wireshark does a very nice thing, very nifty, very helpful. It's like on the number column, you can see the arrow going in and out. So I can immediately understand, oh, you know what, this packet is actually a response from this packet. Or if I pick a random one, oh, okay, this is the request, this is a response. It may not always be intuitive, but you have to understand that right now I'm filtering with ICMP. If you don't have any filter, or if the communication is spread, or even if the response is in multiple packets, you would actually see that arrows are really, really helpful. So let's look at the first request packet. Let's expand this. So just as an overview, right, if you see ICMP, Internet Control Message Protocol, it's actually sent as a part of IPv4. Okay. Now here, if you remember, we mentioned the request is a type 8 code 0. So the moment a system sees a type 8 code 0, oh, you know, it's actually a ping request. That's understandable. Okay, so those are 2 fields, and checksum, that's validation. So let's ignore this. That's fine. Now here's an interesting thing, right? There's an identifier BE and LE. So BE is actually big endian, little, and LE is actually little endian. So it doesn't matter which one you follow. It's just that whatever the system or whatever you prefer, you can use that. If you notice, there is also the same thing happening in sequence number. So B 0 sequence number, and for LE also is 0. Same thing. It doesn't matter which one. You can pick one and stick to it. So if you're going to follow B, then follow B on the reply side as well. All right. Now here is how all those metrics that you see on the on this console are calculated. So here we can see sequence is 0, and this is what that corresponds to. In fact, if you notice here, I see ID, identifier, and seek, which is sequence 0, and then 1, then 2, and then 3, right? So 0, 1, 2, 3, everything starts with 0 in the world of binary, right? Right. Why do we have 2? Why do we have one identifier, one sequence, and the identifier is the same sequence? Why? I'll give you a moment to think about this. Okay, so the reason we have two is, well, it's like a cross section of finding the packet, right? If you have just sequence numbers, okay, great. You can probably find the response, you can correlate and map it to which request it is. But assuming that's only one stream. But if it's more than one terminal session, right, what I could do is I could probably run another terminal. Let me just do that and then show you what happens if I run, and what I'll do this time is I'll just run a ping for a different server. So we can probably do, let's do facebook.com, again, same 4 pings, and I'll run the same thing over here. And let me just start the capture before I do that. Okay, cool. So the capture is running. Let's run this and run this. Okay, cool. Let me stop the capture. And now let's take a look. This time we should have 16 packets, and we can actually verify that over here. It says displayed 16. Great. All right, so 4 requests plus 4 requests times 2, 16. Now let's take a look at this. What's happening with the IDs and sequence? So I ran the the ping from 2 terminal sessions, and I can see that one has an identifier of hex being 0x409A, right? That's the decimal for it. And the other one is 969A. Okay, so this is how it works, right? You could probably run 10 terminals on a Linux or a Mac and run 10 different ping commands, and all of them will be unique sessions. So the uniqueness is identified by an identifier, right? If I were to run a script or do it manually somehow to run ping simultaneously, and if I was just looking only a sequence number, they would probably be the same. So like if you look at this, we have sequence 0 and then 1. Okay, we have 4 packets for sequence 1. We have 4 packets in sequence 2. So imagine if identifier did not exist. How would the system know for which request should I send this reply, or for which request this reply belongs to? And that's why this cross section of like, okay, we have an identifier, now I can match the sequence number. Okay. Oh, and for the again, I'm just looking at the BE, the big endian. If you could just reverse that, it becomes little endian. So it's like from where you look at it. So yeah, don't need to go too much into it. Don't worry about it. It's like 969, it becomes 996. So you can just stick with one. I prefer big endian because it seems more logical. You start with 1 rather than the 256, the high one. Okay, right, another thing. So hopefully that makes sense about identifier and the sequence number. I want to mention one thing here though, that if you're doing this on a Mac, so I've explained for Mac and Linux that the identifiers change per ping process or ping session. But if you were to do the same thing on Windows, open 2 command from Windows and run the same ping command, the identifier is fixed. Yeah, I don't know, just ask Microsoft. So they've actually defined that as a single ping process, so the identifier is always fixed, and that's based on which operating system you use, like Windows 10 or 11 or whatever. So that does not change. They do all the tracking through a sequence number. So yeah, think of it like a single stream where all the packets are tracked, and then they just do it based on that. Which is better? What makes one better? I don't know. It really doesn't matter. What matters to you as a troubleshooter or as an administrator is that your ability to understand which packets go missing and then correlate exactly with the timestamp. And that's where the use of ping is realized, right? You're actually looking, okay, you know what? We have some drops, some intermittent drops. Okay, these packets get dropped, what time? Then I can probably look at my other traffic, if there's any correlation or any event that happened, any incident that happened. Okay, but that's a topic for another discussion. Hopefully this makes sense. This makes you understand, like, this is how I'm going to track, right? It's mostly just a sequence numbers, and then you could also probably need to look at identifier. Okay, moving on. Well, the Wireshark actually is very helpful. It also mentions, so anything, by the way, anything that is mentioned in the square brackets It's actually a Wireshark created thing. If it's not mentioned in a square brackets, that's a packet level, that's a header thing. So type 8 type code checksum, all this exists like on the wire, like it physically exists. But all these square things, well, this is Wireshark's calculation or intelligence. So it does a very good job for response. It's telling you, oh, look, response frame is in 55. So, oh, okay, cool. That's what the arrows are doing same. It really helps in other packets as well. So yeah, just pointing that out. Now, you might have noticed we have another thing over here with the time mentioned. So this is time, which is the same thing as round trip time. So what the terminal does is actually going to send 4 packets, going to get a response, the round trip time of the response. And then what round trip time means is like I send something and I got it back. That's how long it took for the whole thing, right? That's a round trip time. And then what any system does, whether it's Mac or Windows, right, it's going to look at some metrics like, okay, you know what, this is your minimum, great, and if I were to average it, this is what you get. Okay, well, this is the max, so just make of it what you would want. You can probably look at it like to see how network performance is, things like that. And yeah, the way it's calculated is actually going to look at the timestamps and then find out the difference. We could do that, but that's like, it's pretty obvious. So if you look at like 14 millisecond, this is a millisecond. So you're going to look at the request and you're going to look at the response, and that's the difference, right? So you can see relative is actually telling you right here 0.01495 seconds. So you can multiply that by 1,000 and then put milliseconds in front of it. That's 14.9 milliseconds, right? That's it. Now the data part, well, the data is not really important. It's actually just random junk. I mean, if you look at it, so let me move this up here. Okay, if you look at data, right, it's 48 bytes that we are sending, and if you look at what we are actually sending, well, some special characters and 0 through 7. Yeah, it really doesn't matter. This data is absolutely garbage. It serves no purpose. It's just like we have to put something in there. We can't send a packet made up of only headers, right? So that's about it for the data for the Wireshark. Okay, let me try and ping a server which may not respond. Let's see, we can do ping server.com, and before I do that, let me just start the capture. Okay. Oh, so we got no response. We can see very clearly that when I type ping server.com, there is a DNS resolution and it resolved to 52.8.126.80. That's the IP, but we got no response. Okay, no problem. Let's just take a look at what happens. So here we can see that we sent 4 requests, we got no response, and that's exactly what we're seeing in Wireshark, right? So we got ping, fail, fail, fail. Okay, and you can see 4 packets transmitted, 0 packets received, 100% packet loss. So this is what you might find when you're testing out stuff and something's not working. So this is what you will see on Wireshark. So we can see my source, again, private IP address, sending to this server.com address, and no response found. Wireshark is kind enough to let me know that, look, there's no response for this. So that's what you're going to see. So there's a slightly different language that you use here, but this is just an example of what it would look if there's no response for a ping request. And let's show you one more thing. So we've been running ping with a very simple option so far. Let me just clear this up. So we have, I've showed you the flag -C, but there are a bunch of options. So what you can do is, this is what you'll see on Mac and Linux and Windows also. You can see most of these options. They might be called differently. So I do, if I want to run an infinite ping on Windows, I'll do -T. But these are the most common flags that you will see. So if you have more than one interface, you probably need to specify. This is very important when we are testing out things with VPN. So you're gonna specify that. If you want to use different TTLs, so you can use that. Packet size. These are all customizations that are available. Once you are looking for testing out stuff and you want to play around with ping, it's actually a powerful tool. And yeah, these are all the options that you have. Okay, I think that's about it for ping. There will be other videos, hopefully, maybe making use of ping and showing you. So it's very important to know about ping as a tool. Hopefully you like this video and hopefully you find this useful. If you want to watch more of this stuff, then please do consider subscribing. Thank you.